My name is Jörg Mische and I work on the University of Augsburg, and last year I already introduced the reduced complexity many-core architecture we are using here. So we are doing research with it, so this is what me and some PhDs are doing. But I think it could also be interesting for open source and to play around with this architecture. Therefore we released it. I finally got it to GitHub. And in this talk I just want to concentrate on the difference that this architecture, the difference of this many-core architecture to the conventional many-core architectures. And the difference is that we use message passing, so distributed memory and message passing. So probably you all know. So for parallel programming, there are more or less two programming methods. You can either use shared memory or distributed memory. So either you have a shared memory where all the communication between the cores is, you put it in the memory and the other core reads it. Therefore you need, if you want to communicate, you need some atomic load, modify, store instructions to synchronize between the cores. The alternative is message passing, so you send messages between the cores, you have some mechanism to send messages, and then you can have distributed memory on every core, so the cores are more protected. That's our main reason for our research, because we want to isolate the cores. From the high-performance computing, we know that with shared memory, it doesn't scale very well. We see it, so we have it at 8 or 16 cores, and beyond that, it's really hard to get to scale the architecture. Maybe you need hierarchical things or something like that, but it's really hard. For message passing, we know from HPC that this scales a lot much better. And what we're trying to prove with this project is that even in many-core on chip, this also can scale better. There are already, when you look at a chip, you always have something like that. So for shared memory, you typically use a bus. Now there are chips that using a network on chip. This is the idea of sending messages between cores. This is the scalability thing. But what I want to show with this few slides is that this is not enough. We don't can deal with the scalability thing by only just replacing the bus with a network on chip. Because if you do that, this is here, so you just have your memory the bus and you just replace it with some network on chip that connects the cores with each other, and this network is also connected to the memory. This is not, it doesn't solve the scalability the issue, because you translate your bus accesses to memory messages that you put over the network. That's okay, but the problem is not how you send the messages to the memory. The problem is that you have a bottleneck at the memory. That's the problem. In a shared memory architecture, you have there your cache hierarchies and coherence protocols and things like that to get around it. But at least you have, if you really want to put data from one core to the other, you have to translate to transmit it somewhere, and it has some time to come to the memory. So you always have to access the memory, and that's the real bottleneck. So just replacing a bus with a network on chip doesn't help scaling. So what should we use? Maybe an alternative is to use message passing. That's not my idea. A lot of other architectures already tried to use message passing, and the de facto standard for message passing is MPI, the message passing interface. It's used in HPC for years. Standards are for 25 years or more. It's proven, and everybody can program it with it, and there's a lot of benchmarks and programs for it. But there's one thing: it's designed for parallel computers. So the thing is, you have a big latency between your processing elements. So you have a high bandwidth, but you have also a high latency between the cores when you communicate. So to efficiently use this, you have to take long messages to use the bandwidth. This is how MPI is designed, and out of this design, it is not the overhead for sending a message is not so important because you have long messages, and so the sending is not so important. How much overhead you have there. But when we move to an on-chip implementation, the latency between two cores sending messages between is very small, and now you get an effect because sending of the message is very fast, but you have a lot of overhead. So the overhead is really an important part of sending the message. Why is this so? Because how you typically implement message passing, is you have separate message passing buffers. It's a private memory for each core, and there you put your message in. So the sender puts it in the message, and the receiver reads it from this message, or the other way around. There are several different implementations, but the important thing is every core has its own message buffer, and you transfer them with direct memory accesses. You transfer these messages. This is how you transfer the data, and then you need some mechanism to notify the other core that you have sent a message or that something arrived, so some interrupt system or something else, or you polling on a memory address or things like that. You need something else. So it's really a lot of overhead, not just copying the memory to another memory, but also waiting and synchronizing between the cores. So this is really a lot, and now this is what we try with our reduced complexity many-core. What we want to do, we want to integrate the message passing into the pipeline. So we propose some instructions to directly send messages directly from the pipeline. So these are more or less like loads and stores. So what we introduce here, so you simply have 3 instructions to send and receive, and the idea is that the message is the word size. So for example, 64 bytes. So you only send messages at the word size of the processor, and then you can simply have a send instruction where you have in one register your core where the message should go to, and the message itself in another register. And for receiving, you need 2 instructions because you have only one write port to a register. So you just do this first implementation where the message comes from, and then you do the receive the message, and remove it from the receive buffer. What you need also is you have to control your buffer. So if you have a send buffer and a receive buffer, but you have to control, is it full or is it empty? Has a message arrived? In our first proposals or in first ideas, we did this with a status register, and you read this register and then you do a loop. But when we really implemented it, it's much easier for us to implement it directly as a branch instruction, because we have the signal and you just put it directly into the architecture. So we just have 2 signals if the receive buffer is empty and if the send buffer is full. And according to this signal, you have this branch instruction. So if the send buffer is full, it's not ready. So you have to branch the other way around. So with the first instructions, you check if the send buffer is full, and with the other, if the receive buffer is empty. So you can control it, and you have to do such a loop before you receive a message. You have to loop and wait until a message has arrived. And this is really easy to implement. So we implemented it, and we have a classical 5-stage pipeline. And to integrate it, it's really easy. So we have this router, and the only connection between the execute stage and the router are 2 FIFOs. One for sending and one for receiving. So you simply connect this with the execute stage, and you can easily implement this because you have nothing to do. and you simply have two signals for the empty and the full for the empty and for the full FIFO to the decode stage, where you decide if you want to branch or not to branch. And this is why the idea, because we, sorry? Question? Is far of the? I don't check that that it's received. Sorry, I didn't get the.
So the question was if it's fire and forget. So you.
So the fire. Yeah, fire and forget. Yeah, because you are on chip, you have the guarantee that it arrives. That's also a difference to the MPI interface, where you always have this acknowledgement messages that it really arrives, because we assume that we have a reliable interconnect. Yes. At a higher, yeah, you can do this at a higher level, or we're using it for real time. So if with this real time, we have guarantees that the message arrives in a certain time, so we know when the message has arrived. We have these guarantees. That's how we use it in our. But you can also do it on a higher level on a protocol where you do this. So we implemented, for example, we implemented MPI, and there we had to do this, all of this acknowledgement messages and all this stuff.
I'm not sure where you got the idea to work this way from, but have you ever looked at the transputers and the XS1 implementations?
I know this is not a new idea, it's just a little bit different. Yeah, I know in transputers they did it all, but they had even a more integrated, they really registers within, I'm not sure if is this transputer where it's really a register and you write to this register, and it's really hard to program such an architecture. I know about it, and there's how you did it.
Register, it was a memory map approach.
Yeah, so you had memory maps for each direction, like north, east, south, west, right? And then it was like memory
next
map.
slide. On the next slide, how we, the interconnect we have. So this is the connection to the router, and then we have on top we have a NOC, also special because we need a real-time capabilities. It's also in this reduced complexity, so very simple NOC. We don't use a mesh, we use a torus, and it's only one directional. So this reduces, we don't need 4 connections to every side, we only need 2 output ports. So maybe, but this has the downside that if there are neighbors, at least you have to do a round, but this is the downside, but we, it's very, the complexity is very small, so we need very small hardware. And the idea is to just do XY routing and to constantly transfer. So when you enter the message to this, so you have these rings in horizontal and vertical direction, and once a message, because a message is only for one cycle, so we transport in every cycle one message, and so you don't have to you don't need buffers, so you can transport it in the X and the Y routing without any buffering or without any stop in between. Only when you change from X to Y, you need a buffer because you have to wait until there is a free slot in this. The algorithm is a little bit more difficult. I could do a own talk about this, but so for just to see the principle is that we need 2 directional, 2 ports and unidirectional torus.
Yeah. So how can you guarantee? How can you make it predictable? If you've got something on the left-hand side trying to send to the right-hand side, how do you know there's nothing being sent by something in the middle? So doesn't the, aren't you...
You just, you listen on the, you have this ring and you listen and you wait until there's something free. So there's a problem. It could be that it's full. That also, if the node directly before you constantly sends something, you have no chance to send.
Yeah, so But it can't be predictable then, because...
Yeah, these are two. We have, when you're predictable, we have two versions, a predictable and a non-predictable. On the predictable version, we do this with time division multiplexing. So depending on where you want to send your message, you have a time within a period when to send it. Okay, and so it's guaranteed that when at this point, when you send at this point, then it's guaranteed that it won't collide with another message.
So did you look at the Pico-chip architecture?
A
company called Pico-chip. They did a time multiplex network.
Yes, I know this. I've heard about it. They have something, but I think I haven't heard for a long time from them. I think they are. It's the same like with the Talera chip.
Intel now.
Sorry?
They're owned by Intel now.
By Intel.
Yeah, they got bought by Mindspeed, and then they got bought by Intel.
Yeah, I never found something more about it. I found some public.
Already.
Okay. Maybe we could talk later, but I have heard about it, but then somebody got silent and I didn't hear anything more. It's still okay. So this is the network on chip, and the idea is that to have a very simple router, and that's it. So it's more or less only a buffer and a few multiplexes, because all you do is when there comes a message in from south or from west, you just forward it. And only if there's no message, then you can either add one from the local in or from this buffer where you have, or if it arrives at the correct core, you go out to the local out. So it's not much hardware, so 500 logical elements. And here this local in and local out, this is the connection where you connect it to the two FIFOs and then to your pipeline. And all this together forms the reduced complexity many-core. So the idea is to have the simple pipeline with we use RISC-V ESA, and our core we have implemented itself, but it's comparable to the Rocket chip. Then we have only local memory and this network interface, what basically are two FIFOs, and then we connect this with the Paternoster router to a big many-core. And the idea behind this to have a lot of cores, to have a lot of parallelism and get the performance from this parallelism. We won't, it's not a solution for every problem if you have much of sequential code, but for really parallel programs, it should be an alternative. And so we're using this architecture, and we have two main research goals. One is this with this parallelism, so we trade the core complexity for a large number of cores, and for some problems we think, or for some program classes, this should be a good solution when we have a lot of parallelism. And it's some kind of what you're doing with GPUs, it's some kind of the same thing. You have to change your programming behavior, but you get a lot of performance from it. And our main research goal is in the real-time domain. So we want to calculate the worst-case execution time in a parallel system, from parallel programs, which is a real problem in common multi-core architectures. Even with two cores, it's really a mess to calculate the worst-case execution time, because you have this interference between the cores. When they interfere at the memory, it's really hard to get an upper bound. So there are a lot of people working on it, but we ourselves had a program where we did it, and I did it in my PhD, and it's really hard. And so this is the alternative. So don't get angry because of this shared memory architecture. This is an alternative, and we look at it if it could be an alternative for real-time systems. So what is the current state? So we have an FPGA prototype with 4x4 cores. RISC-V architecture, but only the integer part is implemented in VHDL. But so the core, including the buffers, needs about 2,500 logical elements, and the router again 5, so 3,000 for one node, and so we can put 16 on a core on a cyclone 4. It fits there, and the code is on GitHub now, and. But for our research, we want to dig into how is it for larger core numbers. That's the more important, the more interesting thing. Therefore, we have a simulator in-house. It's written by ourselves, and what we did in the last year is to really get a cyclically accurate simulation. So. We had a student there, and now, so our last test is that we had this Ocean program. It's 16 threads, every running on one core, and it runs for about 6 million cycles, and it's really identical on the simulator and on the FPGA. And with this simulator, we also support floating point and all the other stuff from the RISC-V instruction set. And what we also have finished now, we had 2 programs where we could really calculate a worst case execution time. And but these are very regular parallel programs, and now we are looking in what are the kinds of programs that have a acceptable performance and where can we calculate a worst case execution time. So that's it from my side. So I told you what the reduced complexity architecture is. So simple cores with local memory and message passing connection, and this paternoster knock, which is predictable if you want, and how pipeline integrated message passing works. And you can find all of this in our GitHub repository. But for the pipeline integrated message passing, we have an old version there, so you have to wait a few weeks until we upload the latest version of it, because we have to verify everything and so. But I will do this soon, as soon as possible. So thank you.
Yeah, thank you very much. Let me take the chance that I have the microphone already. I have a question regarding, so it's a good solution. In message passing, you distinct between eager and bulk, right? So this is like, it's a perfect solution for scalar communication. But most problem sets are not scalar in the end, right? So if it's an image, if it's something like this. So how do you cope with, like, maybe try to make it short, and, but is there like an efficient solution to do like bulk transfers using the scalar approach? Because I would imagine it like you load it from memory, do some processing, and immediately fire it out. How do you know that the destination is ready to receive it? Isn't it like kind of gang scheduling behavior that they are like going in like log sync about processing pixels and stuff?
It depends on the program. It's a problem what application you will use, and I think it's a real problem, and I said it won't be a solution for everything, but we are focusing on this real-time aspect. And if you have a program where you can, in principle, calculate an upper bound for the execution time, it has to be very regular, and you have also, on the others, if it's not that regular, you won't get an upper bound on principle on any architecture. So you have very strong conditions on a program to be analyzable, and we hope that if we have these restrictions that come directly from the analysis side, this fits good to this architecture, so that these programs are so regular that you can use it in such a simple architecture.
Okay, thank you. Yeah, but they were the first, so I keep track of it.
It's inefficient routing. So I'm excited to see the open source release. So currently Maxim is up there, so the software simulation. Are you going to open up the RTL as well?
Yeah. Isn't it? Oh, then
No, there's right now there's one commit from 24
only
days
this.
ago. But
Okay.
any time now.
That's but it will. So
Great,
let
fantastic.
me return to
Excellent.
now we will. Now it should be because it's not much code. So that's the interesting thing. I think this is also for the open source community. So it's the core is not much, the router is not much, the network is not much. So it's really easy to understand the whole system.
Andre Powell again, sorry, but you only have 2 output ports. So
Yes.
that implies the fact that if you want to communicate with the device to the west of the device, you have to go round the torus, which means the fact that you have an incredibly inefficient routing, which means not only inefficient for actually time, but also for power. That stuff is still going to, you still need to light up the lines to actually get there. So you're sucking current out. Wouldn't it be better to actually then sort of have 4?
Maybe. So we will dig into this because this is a solution to it's so minimal hardware that we can take 2 or 3 or 5, 4 of these networks, and maybe we have one in the one direction, one in the other direction, or we use multiple. But this is just a minimum, and we will see how because in these programs we currently analyze, mostly the bandwidth is not the problem.
Well, it's also with the bandwidth, it's also the power consumption.
Or the power, yeah, good for power, but and for this point, you can also for a torus, you don't need this outside, right? You can also arrange it in a different way, folded torus. So then you have only between the cores you have double the distance, and then you can use a folded torus.
And what if a packet, the word comes in and that buffer isn't available? What happens then? I.e., a word comes in. Meanwhile, there's actually at the same time you have a collision of two words coming in at the same time.
Then you take an extra round in your.
So you have an overloop that you then start around again.
You have decide. We have 2. We have this best effort implementation and this real-time implementation. We have 2. So if you have this best effort, then you just take an extra round. You have to wait, and so you have back pressure on it. And on the real-time side, we define the times when you may send, and there we avoid that the buffers get full.
That's what the Pico chip did. Yeah. Okay, thank you.
While I carry to the front, maybe on the power side too, if I understand it correctly, the receiver has to pull for incoming messages by branching, like in a loop, right? Are you thinking of like some wake-up mechanisms instead, like blocking?
I thought about it, but the solution would be if you have this message, this branch already, you jump to yourself. You have a instruction just waiting that some message arrives, and you can in the decode stage you can recognize this, and maybe you can simply suspend your core. So you just turn it off and wait until some message arrives. So this should be some optimizations.
Right. What's the programming model?
The program?
Yeah, so how do you, as a programmer, how do you specify communication? I mean,
you can use, for example, what we're currently doing, we're taking MPI programs, for example. You can use an MPI program, but it's not the ideal way. For that, we are looking into parallel programs and try to dig into it and find this is another project we find, so parallel patterns, and implement these patterns in a special way exactly for this architecture. So to simplify the programming. For example, we have students, we give them a shared memory program, and then they should try to port it to this way, and we try to learn what do we have to do, what should we do to simplify the programming of such systems.
How does the program get partitioned onto the core,
currently we have the same program on every core, simply.
Okay.
But we can do it in a different way, but currently this is our first step.
So one quick last question.
Before by HOR, with communicating sequential processes, right? So it's just an implementation of that, and there are
this is another idea,
examples.
to port these CSP programs on it. Yeah, that's another idea. Yeah, this program model of CSP to port it on this. Yeah.
Okay, Dan, thank you very much. Let's thank the speaker again.